So, so let's get started. And we just trying to finish off the lecture from last week regarding the motor drive system. So this one is so-called the vector control we mentioned last week about when we control a motor, then we can able to use so-called the field on wheel control FOC, this method. We can separately to control the torque and also the speed. So for the torque and speed here, we are able to control amount of thrust going into the motor system and also the torque per system. So these two represent the torque current and the thrust current. We are able to control that. So after this, then we look next thing we look into will be the field on the control. So you can see that this control, we basically have a motor in here, try to make the FOC control more look like a motor. So that's to say we're able to control the field current to the field winding and also armature current. So that means FOC, although we try to control a motor, but actually we try to control DC motor method to control FOC system. Yes. How do we turn off the script? Now they can able to provide the script. Since I don't know how to turn off anyway. So lastly, we also mentioned about the SR motor, switch reluctance motor. So this one is based on the reluctance principle to drive the motor rather than to use the magnetic thrust interaction. So this one, although the magnetic thrust will go through the motor, but this motor basically they try to minimize the reluctance for the motor system in order to provide the motion. So that means you can see here, we try to transfer the magnetic thrust into the motor so that when the thrust go through them, we try to go through the minimum magnetic thrust. If we energize, so this is the winding. This is the winding. When you energize them, then the magnetic thrust will go in here. You try to complete the loop. All the magnetic thrust line current, we still need to fulfill a loop, a closed loop. So then the magnetic thrust in here, you therefore pass through in this loop, going back in here, if you energize this coil and this coil together. So they try to minimize the thrust here. So if they are in alignment, then the thrust will go through them more properly. But if they display a little bit right in the angle, then the alignment force will force the motor to rotate until become an alignment here. So that's how we use this method to control the magnetic force to minimize so-called reluctance. So this magnetic path, we call them the reluctance. So we try to minimize the reluctance. So that is the motor motion here are based on the reluctance principle. So that's why this time machine we call them the switch reluctance. So the arrangement here we got 6-4 means 6 in the stator and 4 into the rotor, and 8-6 means 8 will be in stator, 6 in the rotor. So detail of the operation will go through in more detailed classes, but here it just show to you we do another type of motor, which is based on this kind of the reluctance principle. So the key thing is you can see that when we rotating the motor, then under the alignment in here, under this alignment, then we are able to have a largest inductance. You see there's a winding here and also magnetic core. So that means then will create the inductance if you try to measure the winding. So that's to say, when we rotate them, the inductance will vary with the position theta. So that's why I can see that when the winding are not aligned properly, then the inductance will be small. When they align well, then the inductance will be largest. So the way to change the inductance actually highly relate to the torque for the motor. Later on, we do have the equation to show you the torque are related to changing rate of the inductance. So that means what we're trying to say here would become alignment. So here will become not aligned. This face is not aligned because this is not facing the pole, the metal pole. So they are not aligned. If the first one to go through here will be really high reluctance. But if the first go through here will be much shorter reluctance. All the metal here are silicon iron, they really conductive to the metal first. But we still need this alignment so that they're able to conduct the metal first. So that's called alignment or unaligned. So that's the how we talk about in here, aligned and unaligned. So here the picture I also showed last week, how the flux being changed. So when we energize this motor, we turn on these two transistors to energize this inductance. When we turn off these two, the inductance will continue to flow back to the DC side. So it more look like we energize them and release the energy back to the source. Of course, under the motoring, we need to put more energy into energizing the inductance. And then the energize only return any excess current. So that's how the motor operates. So here we can see that. So that's why this motor will be really good when we want to use the motor for motoring or even though as a generator. Depends on how we configure the motor, how we control that. So that is to say, when the slope is increasing the motor under the motoring, so we input energy to the motor, and then in here they will generate the torque. Conversely, if we pass through the alignment, the motor continue to rotate, then become unaligned. So energy stored inside the winding in the dynamic, then you return back into the battery. So that's how it look like. So that means in this part, it more look like motoring with the power from DC to the motor. This part will be so-called regenerating, the rotating mechanical dynamic will return energy to the battery. So we can actually control how much you turn on, how much you turn off in order to control motor, more like motoring or regeneration. So that's to say you can control motor, more power, like a motoring torque, or reversely, that the reverse torque will become a braking. So that's how they basically operate. You can see that the torque equation in here relate to change of inductance and also relate to the square of the current. So that means high current, high torque, and vice versa. Also linearly proportional to change of the inductance. So that means this slope is proportional to the torque as well. So if we have sharper slope, high change of slope, then we can able to have high torque. So that's one way to look into.
How did regenerating portion work?
Sorry?
How did generating portion work?
Now that's a very good question. The motor, supposedly when the slope is rising, then you provide a positive torque to drive the motor. In the regenerator, because the slope is negative, then this one becomes negative torque. So that means we try to get better power from the wheel. That's how it looks like. Of course, when you're motoring, then we want to have more portion of this one. This one, we try to have a shorter duration by controlling the turn on angle or turn off angle for the transistor. Because we got two transistors, we can control how long is spent in here, how long is spent in here. So that's how we can control. So however, if you want to as a generator, you're able to have more duration spent on the generator so that you're able to track the energy from the dynamic movement back to the motor. So that we need to turn on, turn off here. So that's really an interesting topic. Of course, we are not going to cover it here because that relates to another new piece of the topic in electrical machine, not in this lecture. This lecture only shows you brief concept. We have a motor called SR motor. We have alignment and disalignment. That's it. So bear in mind, it's too complicated topic. This topic will take me also take a few months to study properly. In here, I just showed you briefly how they look like, and the basic equation. So in the future, if you come to my EV course, more advanced level, or come to my electrical machine course, then we'll talk you all the machine design, how to design this one properly. But basically, this motor can be for motoring and also for power regeneration, depending on which region you want to operate. All right. So here will be say that because here's the motoring right in here. The rate change of speed, this slope relates to the motoring, and the current also is proportional to current squared. So the current is here. Then how we control the current to be constant, because we want to control certain amount of current to a certain amount of torque. For instance, if I want to overtake a vehicle, we quickly inject more current. And how we going to inject more current? So we got our so-called the current profile. We use the transistor here, turn on and turn on, control how the current go into the winding. So what is happening here will be like that. You turn on, so the current will go up in here. When you turn off this two, the current will dropping. So that is to say, I can use this mechanism to control my current for this. You turn on, the current will, then turn off, the current will be dropping. Turn on, increase, turn on, dropping, so we can control this on, off time, on and off time, to adjust amount of the current level. Although you may say this current has this kind of the triangular form zigzag ripple, that's okay because we are using really high frequency to drive them. This ripple actually will be quite small. So that means we are using this method to control the current by turn on the transistor. We increase the current, turn off the transistor, to allow the current to decay through the two diode here. So that's the way we can control the current. So that's why we can using this method. We want certain current level, we just turn on, turn off, turn on, turn off to control the current in this region. So that's how we do the current mode control torque. So that basically you can see how we control that. But you see that if the motor is running slowly, of course we didn't adjust the current really well. So this slowly, that means this time period may be long enough. We can keep turning on off the current to do that. But however, if the motor running really fast, as I mentioned, this motor, the fastest motor in the world, also this motor. So that is to say, such a high frequency, maybe this is only about one millisecond. You don't have sufficient time to switching a high frequency, maybe this is only 0.1 millisecond. So with high frequency switching may not be feasible here. So in here, we just turn on, turn off. We just calculate how much turn on time, and then when to turn off. That's it. That is mainly for high-speed rotation control. Then we use this method to do that. So anyway, we are not going to go through too much detail of SR motor. You can see this to show you. Our SR motor are basically working on DC voltage. It cannot inject any AC. Like industrial motor, we can inject purely AC. Then industrial motor can rotate by itself. But this one cannot. We only need DC operation. We also need an inverter to control the two transistor operation for the inverter. And then this kind of the motor and generator can be done simultaneously in the same kind of motor. In one region, operation is motor. One region operation is generator. So this motor is really well for both motoring and power regeneration. And the thing is really robust. You can see the motor only have winding in the stator. In the motor have no winding. And the whole structure just metal, silicon iron. So we don't have any particular multiple winding, very complicated winding. We don't have any complicated control method. So this motor really good. We call it simple and robust. Inertia. Why this motor have low inertia? Anybody can give me a hand? Why this motor have low inertia? No winding. No winding. True. The rotor, the rotating part, only silicon iron. No winding there. So it does not increase any heavy duty, heavy load there. So that's why this motor have a really low inertia. And as long as a motor low inertia, then that means dynamic performance. How to speed up, how to reduce speed will be much rapid, much faster than all the other motor. You see, for all their motor, for instance, for DC precision motor, they have a PM permanent magnet in the rotor. That is something can increase the inertia. Now, industrial motor, the rotor do have the rotor winding that can also increase the inertia. So that's why this motor have high reliability. And why high reliability, as I mentioned before, this motor, say this three-phase motor, even though by any reason this phase is broken, like this is broken or the line is broken, we still have two phases. So we just losing out this power, 1/3 of power, we still have 2/3 of power to continue to operate the motor. So maybe the motor rotating, if this way, this line is broken, when the motor rotating here, you may not energize anything. In here, you just have higher ripple. The motor still rotate past through it, so we use the other two phases to control the operation. So that is to say, this motor can be more reliable because each phase are independent from other. It doesn't like industrial motor, three-phase system, all the three phases need to be balanced. If not balanced, it's not working. So industrial motor highly depend on the three-phase balance. So any one winding is broken, you cannot do anything. You cannot rotate anymore. But for this one, you can. So that's why for three-phase drive or even a four-phase, we are really comfortable for the operation, for the safety. But we do have disadvantage. We can't have perfect condition for everything. The disadvantage will be we need more complicated joint. Why I say more complicated? We still need two transistors, right, for the inverter. Why you say more complicated joint? Anybody can give me a hand? Why it's become more complicated joint? Why more complicated? Do you think this joint are more complicated? Let's look at it again. Do you think this drive is more complicated? It's still two transistors per winding. All the inverter have two transistors anyway, right? Per inverter leg. Why
Maybe
this
because
one?
of the timing, like
Say-
which one have to turn on and which one have to turn off.
Hmm.
Because it's complicated because of that.
Yeah. If you look at the conventional inverter, right? This is the DC. And then this is connected to the winding. Of course, the transistor always here and here. The number of components between two are equal. Two transistors and two diodes per inverter leg. But however, this side is connected. So when we buy any inverter modules, they have configured in such a way. They don't configure in such a way. That means this point, they are not connected. So that means because 90% or 99% of the inverter module in the market are using this one. If you want to buy this one, you need to pay more. You need to specially make. And then, although I should not say it's really complicated, but it's just the configuration here may not be too welcome for conventional power module we have been using. So that's why for this one, although I think it's the same, I think will be simple. But for the engineer point of view, because not yet in the mass production, we need to use more complicated method to put them together into the SRM system. And then you also need sensor, of course, sensor. You need to detect which rotation the rotor is in, and then we energize that corresponding winding. When the rotor pole rotate to here, when it close to the alignment, then we energize the particular winding so that you can able to control. So that means we do need a sensor. Industrial motor, we don't need any sensor. Sometimes DC motor, we don't need any sensor. We just put the DC or put the AC into the motor, it can rotate by itself. But for this one, we do need to understand the exact position. So we energize the particular winding. And because this one, then the top ripple may be higher. Yeah, this motor are famous for the high top ripple. The thing you can see that this current relate to the top. And then this is constant top. But when the current being decreased in here, this is also related to the top. So we got very nice top here. But between from face to face, we pass through this region. This region, the top is not linear. So that's why we got good top, but suddenly we got lousy top in here. And also when the motor rotates at high speed, then we do not control the profile very well. the profile is increase and decrease. So this is not a constant current. So that's why the top ripple here also not that good. So that's why this motor supposedly have higher top ripple. But of course, that's only in the old textbook or old story. Today, we are able to use really good kernel control to control the profile. In this case, we're still able to control good top. So this technology already, for my team, already readily built up. So we don't worry about this kind of top ripple issue. Anyway, to conclude what we have said for this lecture, then we talk about the brushless DC motor, which is really popular, has been used in many EV system, but the brushless DC motor may not be too good for really high power full motor system. And then industrial motor is also good. It's very mature now, has been used in many EV. But what I like to do more will be SR motor, switch reluctance motor, because it can able to provide fault tolerance. Fault tolerance will be really important for all the motor drive system. And also, supposedly, it can provide really low costs because the same motor is really simple, then the low cost solution could be feasible. And also, high speed motor can also go to this SR motor. So this motor do have a good opportunity. So here will be some more reference. If you can see, I got many journal paper in this area. If you understand how to operate, and then you can also check all these references. So this is really conventional motor system. So I've been working on this system for more than 20 years. That's all for this session. Any question? If not, then we'll go to the next PowerPoint.